Right. So we stopped here last time. We're still talking about the casting process or solidification process. In the casting, as we discussed last time, if you remember, this is a liquid. We bring the metal in liquid. We melt the material, the raw material. We put the raw material in a liquid form, and then we pouring liquid in the mold. This is what we call mold. We create cavity in the mold. We bring the liquid or pouring liquid in the mold. Liquid will fill all the cavity, as you can see here. Liquid will fill all the cavity, as you can see, and then while solidification becomes solid, you destroy the mold in sand casting. For example, you destroy the mold, you take the part out, so as a solid, definitely. So this is casting process. We're still talking about casting. We stopped here last time, talk about the temperature in casting. Temperature in casting is like this. Actually, the liquid here meaning that you're melting the raw material. So actually, we heating the raw material, not to the melting temperature, but to higher than melting temperature. We heating and melting, we heating to melting the raw material, but we heating not to the melting temperature, but higher than melting temperature. Why? We heating the material to higher than melting temperature. Actually, the reason is, you can see that here, this is the initial temperature, raw material, initial temperature. We heating the material up to the melting temperature. Here, melting temperature, it take a while for all material, because material here start, at this point, start to change from solid to liquid. Then here, need few time to melt or to totally change from solid to liquid. And then we heating again, we heating more, not up to melting temperature, but up to whatever we call it is a boiling temperature. It is higher, boiling temperature is higher than a melting temperature. So we heating the material up to the melting, and then heating again up to boiling temperature. So what is a boiling temperature? Boiling temperature is around 100 to 150 degrees Celsius above the melting temperature. Why we do this? Why we just melt the material become liquid and do the casting? Why we have to heat the material more than melting temperature, or more, some just added some heat after material become liquid? Because when you casting the material, when you pouring material in a mold, the mold is cold. This mold is cold. يعني يا شباب بالعربي ان المولد ده اللي احنا بنحط فيه الليكويد بارد. Once you put the liquid, immediately temperature drop. This temperature here of the liquid material, when you put the liquid material in the mold, temperature drop. Why? Because heat transfer will happen. Because the mold here is cold, not same temperature but cold. Once you put the liquid inside, material start to drop. So we losing temperature. If you just heat up to the melting temperature, if you just heating this liquid material up to the melting temperature, and you pouring material or liquid metal in the mold, immediately temperature drop. If temperature drop, solidification will start. So material becomes solid somewhere, not fill all the cavity. The main idea is that the liquid metal must fill all cavity successfully. The liquid metal must fill all cavity successfully. If same temperature here as a melting temperature, or temperature of the liquid as a melting temperature, once you put inside, material will drop. If material temperature drop, meaning the solidification will start. Probably material solidify here and not fill all the cavity. So to be sure that material fill all cavity perfectly, you have to increase the material up to the boiling temperature, probably 100 to 150 degrees Celsius above the melting temperature. Then in this case, you pouring the liquid, temperature drop, no problem. Because temperature drop, then no issue. We still are in a liquid here. Until you reach this point, still you are in a liquid, then liquid will fill all cavity perfectly without any problem and without whatever we call premature solidification. Premature solidification meaning early solidification or fast solidification that leading to defect in the material. Right. Any question? Is it clear? So we're heating the material up to the melting temperature and then we're heating more up to boiling temperature. So now we realize that the boiling temperature is higher than melting temperature. Right. There are an equation, we call it heat energy equation. This equation to show what is the total heat required to rise temperature to the boiling temperature. What is the total heat required? This is the equation to show what is the total heat required to do the casting process or to reach up to the boiling. We said that boiling temperature. Actually, in heating, we have three stages. First stage to raise the temperature from T0 meaning room temperature to melting temperature. Second stage to melt the material. Second stage means that to be sure that all material changed from totally solid to totally liquid. Actually, it happens usually at same temperature. And third stage is to heat again material to raise temperature from Tm to Tb or from melting temperature to boiling temperature. So three stages. The stage 1, stage 2, stage 3. This is the three stages you can find in the equation. This is a stage 1. Let me just highlight. So this is a stage 1. You can see this is the first part, stage 1. This is a stage 2 here. And this one is for stage 3. So you can see that there are three stages in the equation. Stage 1 here to raise temperature from TO to TM. Stage 2 here to melt the material or to be sure that material totally change from totally solid to totally liquid. The third stage to heat the material from Tm to Tb. Three stages. Okay, one by one. Let's take it one by one. First stage is a Cs multiplied by Tm minus To. Tm is a melting temperature. To is a room temperature. Tm minus To. This is the number of degrees Celsius that you would like to increase from To to Tm. What is a Cs? Cs is the heat, whatever we call specific heat of the material at solid state. Specific heat of the material, this one, specific heat of the material at solid state. What is the specific heat? Listen to me carefully. Listen to me, please give me your attention. Specific heat, the word specific heat, when you hear that the word specific heat, it means that the heat required, this one, specific heat, the heat required to raise unit mass. Unit mass meaning 1 gram. Unit mass to raise the material, unit mass of the material, to raise the temperature of unit mass of the material 1 degree Celsius. Unit mass meaning 1 gram. So you need to multiply by the mass, total mass, which is a rho v. Then you can see that there are rho v here. This is a rho v multiplied by all equation, which is m. Which is m. Rho v meaning, yeah, this is m. Mass of the material. So rho v is the mass of the material. So you can see here. So Cs here, specific heat, means that specific heat is the heat. The specific heat is specific heat is the heat required to raise the temperature of unit mass of the material 1 degree Celsius. It is different from material to material, yes. The heat specific heat for aluminium, different of specific heat of the steel, different of specific heat of copper, and so on. Metal, aluminium, for example, aluminium is a low melting temperature, means the specific heat to raise the temperature is low. If you come to the steel, you can see specific heat is higher, and so on. So specific heat is different from material. So if you talk about certain material, specific heat of aluminium, we know specific heat of the steel we know, specific heat of the copper we know, because what? Specific heat is the heat required to raise what? Temperature of 1 gram of material 1 degree, only 1 degree Celsius. Why we put like this, 1 gram and 1 degree? To put in a table. So be able to put in a table, and later that if you would like to increase more than 1 gram, you multiply the mass. If you would like to increase more than 1 degree Celsius, multiply by the temperature. Then that's what exactly happening. If you multiply by the mass, then you raise more than 1 gram. This 1 gram, this if you multiply mass, you increasing the temperature of certain amount of gram, maybe 10 gram, maybe 15 gram, maybe 1 kilo, and so on. If you multiply by the temperature here, then you raise not only 1 degree, but you raise many degree from TO to TM, right? So this is the first part in the equation, CS, which is the specific heat of the material at the solid state. The last one is exactly the same, CLTB minus TM, TB minus TM, boring minus TM, give you the amount of degrees Celsius that you would like to increase from the melting to boring. This is the TB minus TM. You multiply by CL, the specific heat of the material, same material. Definitely this is same material from beginning to the end. This is the same raw material. So CL is specific heat of this material, but in the liquid form, because we have CS and CL, specific heat in solid state, specific heat in a liquid state. So specific heat of the material in liquid state, is it different? Yeah, different. Different specific heat of the material as a liquid, different from specific heat of the material as a solid. So this is a CL multiplied by TB minus TM as a specific heat of the material to raise temperature from TM to TB. HF here is related to this area. This area we call this one heat vision. Vision per unit mass. Heat vision per unit mass, then what we multiply by mass here. You can see heat vision per unit mass, then unit mass meaning 1 gram, meaning this is the amount of heat. This is the amount of heat required to melt the material, to change the status of the material from totally solid to totally liquid. And this one is per unit gram, meaning, or unit mass, which is a 1 gram, then you multiply by mass here. Then you can see that mass multiplied by all these kind of terms in the equation. Right. This is the heat equation. Here you can just get the heat required to melt the material or to heat the material up to not only melting but boiling temperature. Right. Let's take an example and see how to apply this equation. Right, example 1 cubic meter of certain eutectic alloy. Eutectic alloy. The word eutectic alloy actually, when you said eutectic alloy, there are a meaning. Let me show first what is the eutectic. Eutectic alloy, if you have alloy, this is a pure material B, this is a pure material A, this is the alloy A plus B. All this area in between A plus B. Then in A plus B there are a 1 point. There are a 1 point here. This point, at this point, the melting temperature or material change from solid to liquid at certain constant temperature. What about here? At different point, if we're not focusing here, if we're focusing here, you can see that there are a difference. Here, for example, you can see that material is solid, and then here material is liquid. This is the liquid state, this is a solid state. What in between? In between here, there are a mix between solid and liquid, and there are a range of temperature. Then from here to here, material change from, you can see that range of temperature. Then you need to increase in. Why it happened? Because when you said alloy having two materials, this one material and another material, when you mix two material, this one have certain melting temperature, this one have different melting temperature. When you start liquidize the material, you can find that material start to be liquid. The first one, which is a lower melting temperature, start to become liquid. The other one, higher melting temperature, is still solid. When you're heating up, the other one start to become liquid. Then you get mixed between solid and the liquid, and then you finally both become liquid. Then you both become liquid here. So eutectic, when we talk about eutectic, there are a certain percentage between A and B. Material will be melted, totally melted, or change of totally solid to totally liquid at certain point. We are not focusing on that. I'm just telling you what is eutectic. This is a material science, and we are not focusing. We are here in manufacturing, but just I'm trying to explain what is the meaning of eutectic. So eutectic alloy means that material will totally change from solid to liquid at certain temperature, at constant temperature. No change here. It's only 1 point, as you can see here. So no change in temperature. This is the meaning of eutectic alloy. So 1 cubic meter of certain eutectic alloy will be heated. When you said eutectic, we talk specifically on certain point, certain, I mean, percentage, A and B, so certain point, will heat it in a curable furnace. There are a type of furnace we call curable furnace from room temperature. Room temperature usually 25, 20 or 25 degrees Celsius to 100 degree above the melting temperature. So we heating from room temperature, not to melting, but 100 degree above melting. This is a boiling temperature. So boiling temperature here, we can understand that boiling temperature is 100 degree above the melting temperature for casting. Density is for this material, density 7.5 gram per cubic centimeter. Melting point 800 degrees Celsius. Melting point 800 meaning boiling temperature is 100 degree above the melting temperature. Specific heat is 0.33 joule per gram. As I told you, specific heat per gram, 0.33 joule per gram degrees Celsius. Per gram meaning per unit mass, per unit mass for 1 degree. So you can see that it is 0.33 joule per gram degrees Celsius, because here it is this 0.33 joule required to raise 1 gram 1 degree Celsius. So per gram and degree Celsius. So 0.33 joule gram degree Celsius. This in the solid state. So this is the CS, and 0.29 lower definitely in liquid state. So this is a CL. So this is a CS, this is a CL, and heat vision, which is HF. This one heat vision is 160 joule per gram, because 100 vision is only function of no temperature, because here almost temperature is same per gram. So someone said that, okay, this you talk about eutectic alloy. Yes, I'm talking about eutectic. Let me finish this one and we'll discuss if it is not eutectic alloy. Actually, we don't have, this book didn't describe how to deal with this kind of cases if you have range of temperature. So it's kind of approximation to get the heat. It's kind of approximation. There are other equations to deal with the cases if it is not eutectic, but we are not focusing here. Actually, this textbook that we use just only mention about the heat in case. Actually, the equation in case of temperature is not same and different, is not that far from the equations that we have here. Let's solve this one first. Then you can see that this is the heat vision. This is the CS. This is the CL. This is the melting temperature. This is the melting temperature here. This is the TM is 800. The TB is 100 degree above. TM minus TB. TM minus TB is 100 because it is 100 degree above melting temperature. Then you can apply here. Then you get heat in joule required to do the casting process. Yes. Yes. I'm listening. Muhammad, yes.
Sorry, the room temperature here is 25.
Room temperature here is 25, yes, exactly. He mentioned that it is 25. Mubarak, yes.
Doctor, 10 to the power 6, what is represent?
Excuse me again?
10 to the power 6, to represent the volume or what?
This one?
Yes.
This one? Okay, so this is rho V, right? This is 1 cubic meter. The volume is 1 cubic meter here. Right? So 1 cubic meter is 10 power 6 here. Because all unit is what? In gram per centimeter. So this 1 cubic centimeter, right? unit here are centimeters. See density in centimeter. Either you make centimeter meter or meter. So meter, you change meter here to centimeter, make 10 power 6. You get it? Cubic centimeter, meaning 100, 100, 100. 100
Yeah,
multiplied by 100 multiplied by 100, get 10 power 6, right? Okay. Okay, guys, is it clear? Then in this way, you can apply in the equation, then you get the heat region. Actually, as you can see here, we talk about eutectic alloy. Eutectic alloy meaning the alloy will be melted at a constant temperature. Constant temperature mean if we get back to equation here, meaning that eutectic mean from TO we increase from TO to TM, and material will be melted here. Material will be melted here. Can you see that? Material will be melted totally, change from solid to liquid at what? At constant temperature. This could happen to the pure material if you melting pure material like iron, like copper, like aluminium, and so on, and also eutectic alloy. But if you talk about not eutectic alloy also is okay, which is here. But if you talk about the range of temperature, this equation cannot exactly calculate the heat required in case of we have range of temperature. There are some different equations being used, not this one, but in the book here, only he describe about this equation. But same fundamental and same principle, there are some modification to the equation. Then you can obtain the effect of the temperature as a range of temperature, solid liquid temperature. So this is the limitation of the heat equation. This is the limitation of heat equation. Most of casting alloy melt over temperature range, not constant alloys. If you talk about, if you're melting alloys, then you need to consider range of temperature to change from totally solid to totally liquid. So it is one very important limitation in this equation, as you can see. However, it is just give very good approximation about heat required to boring or to reach to the boring temperature for certain material. Right. Boring the melting metal. بورينج ميلتنج ميتال يعني ايه بالعربي؟ نصب ازاي بنصب الليكويد في الايه في المولد to fill the cavity. This is the issue. This is an issue. For this step to be successful doing this one and successful, metal must flow into region of the mold. Most importantly, the main cavity before solidify. It means that liquid must fill all cavity. If liquid didn't fill all main cavity, it's defect. It's not completed. So I must be sure that liquid will fill all cavity perfectly. So later on, when I destroy the mold and take part out, it will be completed. So for a factor to determine the success, what is the factor to determine success? First one in the boring temperature. So this is the boring temperature. I must heat the liquid up to not melting but boring. If you up to melting, you get the effect, definitely 100%. If you just melt the material, heating the material up to melting temperature, you will for sure you will get the effect here. You must heat up to boring. So first one is a boring temperature. Second one is a boring rate. Actually, boring rate also is very important. If you make it very, very slow, just imagine if you just make a droplet very, very slow, then heat transfer here will become very high. Immediately once it drop come, it will be cooled down and solidify immediately. Then boring rate, actually this whatever we call is a boring rate. يعني معدل الليكويد، يعني معدل الليكويد البورينج ريت، يعني معدل الليكويد اللي انت بتحطه في او يعني اللي بتصبه داخل المولد must be boring rate must be not very slow and actually not very high also as well. Why? Just drop quickly and put everyone quickly, all liquid very quickly. No, if you make like this and you make it very high rate, if the rate is very slow, then you get pure matter solidification. premature. You get premature solidification يعني early solidification يعني will get defect. If it is very fast, also you get defect. Another defect. What is defect? You get whatever we call turbulent flow inside. If you make it very fast, very high the boring rate, very high boring rate will leading to liquid will come inside in a turbulent flow. Turbulent flow يعني mean circulation here. Make here circulation inside, and this one trap air gases inside. And when trap gases inside, this one will be subject to defect like cavity, like bubbles, because this kind of circulation inside will trap gas, and then you get bubbles at the end of the casting, get bubbles, which is a big defect. Then I need the boring rate something in between, not very slow, not very fast. I need it in a lamellar. I need it is in somehow between, so the flow will be lamellar. This lamellar mean layer, as you can see here, homogeneous and lamellar, then it will become fine, and then you get casting without defect. So I need boring to adjust the boring rate. We'll discuss now how to design the gating system to deliver the optimum or to the best condition in the boring rate to avoid having turbulent, and to keep this one in the lamellar, to avoid turbulent flow, to avoid get defect in casting. This is a factor determining success. Okay, important factor in casting are solidification, as we just mentioned, how to solidify, flow of the multi-material into the mold cavity, heat transfer actually, and cooling of metal, which is a liquid metal, mold material. Heat transfer and mold material are related to each other. If you manufacturing the mold of sand, then this one is very low thermal conductivity. It meaning that the heat transfer will be slow, then a material will stay remaining inside for a long time. Solidification will happen slow. If you make the material, if you manufacturing the mold here made of metal, for example, as a permanent cast, if you manufacture mold made of metal here, the cooling rate or the heat transfer rate and cooling rate will be very high. Solidification will happen quickly, and then you have to consider that when you designing the mold, right? Analysis, to do analysis, this is the analysis that we're going to discuss. Analysis for this kind of factor, we're going to do this analysis: fluid, mechanic, heat transfer analysis, thermodynamic, and material behavior, structure, property, and relationship. Then we're going to start one by one. Start with the fluid analysis. This is the beginning of numerical and the beginning of analysis. This is the fluid flow analysis. To remind you, as we discussed last time, this is a mold. To remind you what we had before, this is the mold. Now we're going to do analysis, and we need to do design for all these items. Then to remind you, this is a Bising cup. This is a, here you pouring liquid. This is a spiro. This is the well, gate and runner. This is another runner. This is a blind riser. This is a main cavity. This is a core. This is a vent. This is the open riser. Upper one, which you call it, is the cup. Lower one, we call it the drag. So this is the cup, this is the drag, and this is the flask, which is a metal container to put sand inside. Mold made here of sand. For example, start here, mold made of sand, right? This is the detail of the mold as we described last time. And this one we call gating system. This part we call gating system. This gating system is very important. It is controlling the solidification process and the liquid delivery, controlling the solidification process of the liquid and deliver liquid, how fast, how slow to deliver liquid to inside. Actually, this gating system is not exactly same dimension every time. It depends on the liquid. If you have liquid with slow solidification or a slow solidification rate, then probably gating system becomes smaller. But if you have a liquid with a high solidification rate, mean quickly solidifies, then gates probably could be bigger. Then we will consider that while designing the gating system to deliver. So this one controlling the solidification and controlling the liquid delivery to the mold to fill the main cavity. We will discuss now these items. So the basic principle of fluid flow that we're going to discuss based on which is the Bernoulli theorem and the mass continuity theorem. Two theorem, Bernoulli theorem, نظرية Bernoulli and mass continuity equation. We'll use Bernoulli equation and the mass continuity equation. There are the two types of analysis that we're going to use here in fluid flow to design the gating system. Let me just go through this one. I hope you give me your attention. Please give me your attention so you can understand what is the idea behind and how to do this analysis. Is really very important. So don't miss it. Try to focus. Give me your attention. Don't miss it. Bernoulli, what Bernoulli says. So as I told you, we're going to use two equations, Bernoulli and mass continuity. Then now we start with Bernoulli. Bernoulli equation, what Bernoulli said? Bernoulli said that total pressure equal to constant. Total pressure equal to constant. This is the fluid mechanics actually. This is a fluid mechanics. Mean static pressure plus dynamic pressure, which is a total pressure equal to constant. And Bernoulli said like this. This is a Bernoulli equation from fluid mechanics. Said that H plus B divided by rho G plus V squared divided by 2G equal to constant. So pressure at any level is constant. Pressure, he said like this. Pressure at any level. So pressure is here. Total pressure, I mean. Total pressure is constant at any level. Total pressure is constant at any level, as you can see. Right, so H plus B divided by rho G plus V squared divided by 2G equal to constant. H is the head, head of the liquid. B is the pressure at the point. Rho G, rho is a rho is a density. G is a gravity acceleration. V is a speed, liquid speed. G is a gravity acceleration. This one is constant. This is a Bernoulli equation. This actually is a Bernoulli equation. Let's take an example and see how Bernoulli equation can help in our designing of the gating system in a casting. You can see that this is a gating system. This is a Pising cup. This is a spiro, and this is a well. You can see that here is very similar. You can see this is a big here, smaller, and you get here. So this is 0, 1, and 2. The head of this one is H1. The head of this one is H2. I mean, the up to point 2 is H2, up to point 1 is H1. So you can see that we can apply Bernoulli actually, because here there are a liquid. What liquid? Liquid metal. If you talk about what is inside here, liquid or not liquid. If not liquid, then you can use the fluid equation or the Bernoulli equation. As long as the material in liquid form, you can apply Bernoulli equation, right? So you can apply between any point. Can apply between 0, can apply between 1, can apply at 2, at any point. Can apply Bernoulli equation at any point. So H1, we apply between point 1 and point 2, then H1 plus B1 divided by rho G plus V1 divided by 2G equal to H2, which is this one. This is the H1 plus B1 pressure here at this point divided by rho G, V1 squared divided by 2G, meaning the velocity here at 1 divided by 2G equal to point 2 H2. H2 is the head of point 2 plus B2 rho G. B2 is the pressure at point 2 divided by rho. Rho is constant because liquid same. So same density. We have same density here. And the gravity acceleration also is constant, 9.81. Right, so it is constant, right? So pressure B2 is the pressure here. V2 is the speed at point 2. Just give me a second, Muhammad, and I will let you ask. Plus F. F here is frictional loss in a pipe. We usually ignore. They find that it is not very significant. And probably for simplification, we can ignore the friction loss in the pipes. Yes, Muhammad, I'm listening.
معلش، في البداية أنا ما سمعت ال H1 وال H2. ال
الهيد
H1 بس حق الفتحة، و H2 يشملها كاملة.
H1 بتاعت بوينت 1، H2 بتاعت بوينت 2. الهيد الارتفاع.
يعني H1
الهيد
من الفتحة لين مثلا الجزئية هذه عنوان، أما H2
H1
تشملها
يعني
كاملة.
من هنا الريفرنس بتاعنا اهو، ماشي ماشي، ده الريفرنس. ال H1 اللي هي الهيد الارتفاع بتاع بوينت 1، ال H2 الارتفاع بتاع بوينت 2. تمام؟ محمد سامعني؟
أيوه سامعك تمام. شكرا.
هناخد example دلوقتي، هناخد example. Let's take an example. Let's apply in number and see how to solve in number and how to put this reference and so on. Let's move forward together, right? You can see that there are an example here. As a liquid, water. Now we talk about water. Let's just use water, start with water, and then next is to use the liquid metal and then see how to deal with this kind of things. Let's apply as water for fluid, just fluid, because it is fluid flow. Then velocity here, this is a tank, and there are opening here, a liquid will spill out from here, will move out from this kind of open, right? Like tap or whatever, right? So velocity at the outlet pi, this is the out, velocity is a VA at point A here. Velocity VA equal to 6 meter per second. How we know? We measure it. We measure it as 6 meter per second, and head equals the head. This is the head, huh? Head from this point to point A. The head is 15 meter, right? What is a question? This is a given. So given velocity here given and the head is given. What is the pressure at A? We need to know what is the pressure at A. Apply Bernoulli equation. Bernoulli equation said B1 divided by gamma. Gamma meaning rho G. Specific density. Gamma, which is a specific density, meaning rho G. We said pressure 1 divided by, in the last step, B divided by rho G. Rho G, we can just apply rho G as gamma. Gamma, same meaning. Rho density, G is a gravity acceleration. If you multiply, you get specific density. They call it specific density, which is rho G, which is gamma. So, B1 divided by gamma plus H1 plus V1 square, H1 Z1, same, huh? V1 square divided by 2G. This is the first one at point 1. Here, we apply point 1 here, for example, and then point A, BA divided by gamma plus HA or ZA plus V square A at speed here divided by 2G. Okay, in this case, this is atmospheric pressure. At point 1 here, this is the atmospheric pressure, pressure equal to 0. Here, pressure equal to 0. Relative pressure. We'll talk about it because all are relative, right? So pressure here is 0 because this is the atmospheric pressure. So pressure here B1 is equal to 0. You agree? Then B1 equal to 0. Then this term is equal to 0. And we will consider also the velocity here is 0. Assumption velocity here is 0. Someone will ask me why you do this assumption velocity here is 0, because here you can see that this one will be slow, very slow compared with here, because area here is very big, very small, area here is very small, area here is very big, as you can see. Then there are a speed, actually there are a movement here, there are a speed of movement here, but will become very slow compared with the velocity of the liquid will move out from here. Then usually this surface velocity is insignificant, then usually consider as 0. Assumption to make easier for solution, because finally it is approximated solution, not exact solution. Then V1 will consider equal to 0. V1 equal to 0, right? So B1 equal to 0 and V1 equal to 0. BA, we need to obtain what is the BA. We need to know what is the BA. We need VA, we know here. Velocity of A we have here, which is 6. BA, this is the one we need to know, right? So we need to know the BA. Z1 and Z2, Z1 and Z2, Z1 0. If you put reference here, this is the 1. If you put reference here, if you put axis here, this is your reference. then the Z1 is 0 because this is a reference point, right? I mean axis point. So this point will be 0 0 0 0. That means Z here is 0, Z here is 0, and this is XYZ is here. So Z here is the level, Z here is 0. So what is the ZA? ZA is H minus H actually. So ZA equal to minus H. Or if someone else said, no, I don't want to put reference here, I put reference here, for example. Someone said, no, I would like to put reference here. Okay, just do it, no problem, no difference. If you put reference here, then this is the 0 point. Then ZA is 0. ZA is 0. You agree with me? Then what about Z1? Z1 is H. Either you put here or you put here. Both same. If you put here, Z1 will be 0. ZA will be minus H. But if you put here, ZA will be 0. Z1 will be positive H. So finally, Z1, this is H for Z1 here. You put reference here, then ZA equal to 0, ZA here. Consider ZA equal to 0. This one is equal to H. Then H here is 15 meter. H here is 15 meter. We know that H equal to 15 meters. So from this equation, pressure equal to gamma H minus V squared divided by 2G. Gamma we know for water because water is known. Rho G, rho is density, and we know. So it is 1,000. I mean the density is 1,000. So 9.81 multiplied by 1,000, you get 900. Definitely it will be given. It will give you problem and then give you another liquid. We will give you the density. So no problem, no issue. So this is the gamma rho G multiplied by 15H minus V squared divided by 2G. Then you get the pressure at A. So this is the pressure at A. Yeah, now any question? Yeah, Abdullah, yes.
دكتور السرعة 18 مكتوب، هو المفروض 36.
V square, V square. So because 2G Abdullah هي دي 36 على الاثنين لان دي جي واحده. عايز تحط 2 هنا يبقى دي 36. هو عملها على طول معلش. Did you get it?
Yes.
Okay guys, any question? Any question? Is it clear how to apply Bernoulli equation? So this is a Bernoulli equation. Yes.
Yes, it's clear, Dr. Wow.
Okay, that's it. If you have any question, anytime you're welcome, no problem. So move to our case, casting. Now let's just discuss this one in casting, which is not water but liquid metal. So now what is important for me? Important for me this one is a gating system. So gating system will be like this, right? So this is a Bison. This is a Bison cup. This is a Spiro. This is a 0.1. This is a 0.2. Actually, very important to me, 0.2. Very important to me, 0.2. 0.2 is very important point. Why? Why 0.2 in analysis is very important point? Because at 0.2, liquid will move in a runner to fill all the cavity here in a casting. So usually the main target of the analysis is to get the condition of 0.2. What is the condition of 0.2? As I told you before, if you remember that, how to pouring the liquid inside. Not fast, not slow. Flow rate must be not fast, not slow, to avoid premature frozen in the first case, and second case, to avoid turbulent flow happening in the liquid. Then let's see how to do analysis, in the casting process to reach to this condition. All right. Okay. Then assumption, F is 0. Friction in a pipe here, because it is not big actually, so we consider friction. We can ignore friction, this is a 1. And also velocity here at 0, pressure at 0, and velocity at 0 equal to 0. Then pressure here is atmospheric pressure. Pressure here at 0 here, pressure is atmospheric pressure here, we consider as 0. And also velocity here at 0 point, we consider 0 because you can see that Here dimension is small compared with this one. I mean the velocity here will be slow compared with here and here. So we consider here velocity is 0 or neglect the velocity here. This is the assumption to use. There are one very, very important assumption we're going to consider also. Please listen to me carefully. Please listen to me carefully. We have what we call atmospheric pressure throughout. Atmospheric pressure throughout. What does that mean? Pressure at 0 equal to pressure at 1 equal to pressure at 2. All pressure same equal to atmospheric pressure, because atmospheric pressure at 0 is the atmospheric pressure. So we would like to maintain pressure same for 0, 1, and 2. This means that the pressure at 1 is atmospheric pressure, pressure at 2 is atmospheric pressure. Why we do that? Why we would like to maintain pressure constant all the way through inside from 0 to 2? Why we do this? To avoid what we call aspiration. What is the aspiration? Aspiration is a gas in a mold enter to the metal stream and result in porous casting. If the pressure change from 0 to 1 to 2, the gas will get turbulent here, gas will trap inside if pressure change. We need to maintain pressure constant, 0, 1, 2 constant. If pressure change, if you not successfully maintain pressure constant all the way from beginning to the end, gas trap inside leading to porous casting. What is a porous casting? Porous casting means casting with the bubbles, casting with gases. Casting with bubbles and gases mean porous casting, meaning defected casting. Defected cast means scrap. We're losing the cast. So how to solve the problem? To solve the problem, you need to maintain pressure constant 0, 1, 2, then B1, B0 equal to B1 equal to B2 equal to 0, because 0 pressure is atmospheric pressure. Someone will ask me how they realize that. This is kind of experimental work. They did a lot of experiment until they find that the best casting done when you can maintain the pressure constant from 0 to 2. Right? We call it atmospheric pressure throughout, meaning pressure 0, 1, and 2 are constant, or to avoid aspiration. Aspiration to get bubbles or porous casting. To avoid aspiration, B0 equal to B1 equal to B2. This is the aspiration. To remember that. Aspiration. You must avoid aspiration. You must avoid having aspiration in a casting. This is defective casting. So in this case, I'm going to apply equation between 0 and 2. As I told you, most important to me is 2 is very important point to me. Then I'm going to apply between 0 and 2. Someone said, why don't apply between 1 and 2? Because I don't know the velocity here. But I know the velocity in 0. We assumptions that make V0 equal to 0. Then it's easier to apply between 0 and 2. Then 0, then you can see that B0 divided by gamma plus Z0 plus V squared 0 divided by 2G equal to B2 pressure here divided by gamma plus Z2 plus V squared 2 divided by G. Then we apply between 2 points, between 0 and 2. Then we can see that, okay, pressure 0 is 0. This is the atmospheric pressure. Velocity at 0 we consider is 0 because we said that it is, yes, there are a velocity but very slow. Then we consider as 0 for simplicity of the calculation. Pressure at 2 also is 0. Why pressure at 2 is 0? Because we say that atmospheric pressure throughout to avoid aspiration. So pressure at 0 equal to pressure at 2 equal to 0. Then this one is 0. Then this one Z0 and Z2. Z0 and Z2, this is between 0 and 2. Then the difference here is H2. Difference here is H2. Then put reference anywhere. Put reference anywhere. If you put reference here, let me have, if you put reference here at 2, if you put reference at 2, for example, then Z2 equal to 0. You agree? Z2 equal to 0 and Z0 equal to H2. Someone said, no, I don't want that. I would like to put, okay, just put it here. no issue. Then if you put the reference here, then Z0 equal to 0, then Z0 equal to 0, this one equal to minus H2 will be same. Then this will be minus H2, this will be 0, this one be minus H2. So it will be same. We bring here, it will become H2. Then you apply here, then you get from this one, V square equal to 2GH2, then 2GH2 is this H2, 2GH2, meaning that V equal to square root 2GH2. V2 speed here at 2 equal to square root 2GH2. Actually, this equation is very, very, very important equation. This equation is very, very, very important equation. Why? Because this equation that satisfies the atmospheric pressure throughout. This equation satisfies the condition of atmospheric pressure throughout. When we apply atmospheric pressure throughout, B0 equal to B1 equal to B2, we obtain that speed at this point equal to square root 2GH2. So this is a velocity here. Someone who is asking me how we maintain velocity to satisfy the condition atmospheric pressure throughout. We must keep velocity here at this point equal to 2GH2. Well, this is the H, right? Someone said how we can do this. Actually, that's what we're going to discuss inshallah next class, because time is finished. Have to stop here. The next class I'm going to discuss how we can maintain velocity at this point equal to square root 2GH2, right? To maintain the condition of atmospheric pressure throughout. Okay, guys? Right, that's it. So just before we go, this is another equation here, which is the mass continuity. I will stop here in the mass continuity, and next time I'm going to discuss about this one, inshallah. Let me stop recording.